Hi, welcome back. Today's lesson is 12.4 Conditional Probability. So basically what we're going to be talking about today is when we're talking about conditional probability. So when the probability of something happened, given that something happened before that. All right, so what they're talking about here is, let's say, what's the probability of you eating lunch today when you've already eaten breakfast, something like that. So you're given two situations and two events happening, and you're going to assume one of them already happened. So let's look at an example of exercise 1 by revisiting that two-way frequency table, which talked about males and females either going to college or not going to college. Okay, so this is the same problem we just did. We're going to remind ourselves that male, female, C means going to college, N means not going to college. So keeping that in mind, and I'm sorry, I'm going to have to flip back and forth between these, but find the probability that a person at random was picked. What's the probability of picking a female? Well, going up to our chart, up to our two-way frequency chart, females, 22. So I'm going to have 22 females out of the total of 52. What's the probability that somebody is going to college? That's going to be 29 out of 52. So that's pretty easy to see. Hopefully you see that. That's pretty simple probability. But now, and I apologize, I started writing things here, and let's erase this. Going to college, given that they are female. So how we write that is that P, going to college, given that they are already female, all right? So drawing a Venn diagram below to help justify the ratio helps us see what this means. So we know from up here that there were 22 females that went to college. I'm sorry, 22 females, period. 29 of the people that were surveyed are going to college. But now what I have to consider is this right here, and this is going to be the both of them. So how many people are going to college that are female? So I'm going to slide back down, look at a table. So going to college is right here. Female is right here. So where they meet is right here at 13. So I know that in my Venn diagram, I'm going to have a 13 in here, which means if I take 13 out of this one, I'm really going to have 9 in this side. And if I take away 13 here, I'm going to have 16 in this side. So that's what my Venn diagram looks like. So then it says, which is more likely that a person picked at random will be going to college given that they are male, or a person will be male given that they are going to college? So show the calculations for both. So in this case, I can look and see which one. So college given male. So basically what we're saying is going to college and male. So our numerator, going to college, let's go back up here. So going to college is 16. Out of all the males are 30. So this one's going to be 16 out of 30. Now we're going to look at the probability of male and college. Let's go up here. So we're going to look and see the same thing now, the probability of male and going to college. So male is going to be 16 out of 29. So it goes a little bit differently, use a different direction. Oops, where are we? So this is going to be 16 out of 29. All right? So this way is going to be slightly larger. Slightly larger, this one. Okay? We're going to get into that some more if that was confusing to you. So we can generalize this process to calculate these conditional probabilities based on counts, and a way to calculate these probabilities based on other probabilities. So let's take another look at an exercise. All right. In the generic Venn diagram shown to the right, each dot represents an equally likely outcome of the sample space. Some of these fall only into event A, some only into event B, but some in both. All right. Just like we talked about before, the ones here in the middle, inside here, is the intersection. All right? So consider the probability of A occurring given that B has already occurred. That's how we write that. All right? Probability that A occurs given B. So give a formula for this probability based on counting the number of elements in each set and their intersection. So this is going to be the number of A and B over the number of B's. So divide both of the numerator and denominator by A by the number of total elements in the sample space, then rewrite the formula in terms of probabilities. So basically all this is going to say is the probability of A and B divided by the probability of B. So this is going to be the formula that we are going to, that's going to help us with the next few exercises. So this is what I'm talking about. So a survey was taken to examine the relationship between hair color and eye color. The chart below shows the proportion of people surveyed who fell into each category. If a person was picked at random, find each of the following conditional properties. Show the calculation you used. So A says find the probability that a person picked had brown eyes given they had blonde hair. So we're talking about the probability of brown eyes and blonde hair all over the probability of blonde hair. So the probability of brown eyes and blonde hair is 0.10 over the probability of blonde hair is 0.35, which is 0.29. They're asking for a probability, so the number has to be between 0 and 1. Okay, so that was kind of easy. Let's look at the next one. All right, this one says find the probability the person had red hair given they had green eyes. So this is again going to be the probability of red hair and green eyes over the probability of green eyes. So the probability of red and green, the probability of red and green. So the probability of red and green, that's where I am. So red and green, red hair, green eyes, 0.15, 0.15. All right, probability of green. So probability of green is 0.25. So 0.25, do the math and you get 0.60. Now, it says, does having red hair seem to have some dependence on having green eyes? How can you tell or quantify this dependence? I'm sorry, guys, I can't read today. I should not do these after school because I'm just too tired. All right, so the answer is the probability of having red hair is 0.20, right? And the probability of having red hair, given that you have green eyes, jumps up to 0.60. So the answer here is absolutely, there's 3 times more likelihood to have red hair if you have green eyes. So dependence is absolutely valid here. So you can say this does show dependence since it is 3 times more likely to have red hair if you have green eyes. All right, that's it for today. So not bad, 10 minutes. Okay, we are done with the lesson for today. So I know this is a little bit confusing, but just the only thing you have to take away from this is this formula right here. Understanding that something is happening given something else happening before that. Okay? So that's going to be one of those formulas that we're going to add to our formula sheet because it's something that's not given to us and we have to commit to memory. All right? So until next time, always make good choices and I will see you tomorrow.